Hello, welcome back. This is page 3 of the Unit 4.1 packet. So the goal for this page is to learn how to write formulas and names for ionic compounds. So the first thing, when we're going to start writing formulas, we're going to be given two different elements that are going to be making an ionic bond. And what we need to do in order to write the formula is we need to figure out what charge each of these form, and then we can put them together. So we're going to first find the charge. And that charge of each ion tells us how many electrons an element wants to give or take when making a bond, and we're going to have to piece these together like a puzzle. So for example, if one element is a +1 and the other element is a -1, this means they each want to change by 1 electron. One wants to give 1 electron, the other wants to take 1 electron, and that's perfect. I give you 1, you take the 1, we're done. On the other hand, if we have one element that's a +2, that means it wants to give away 2 electrons, and the other element's only willing to take 1 electron, well, the other electron has to go somewhere. And so this is a case where we're going to have to change the ratios a little bit to make them perfectly fit together, because just one of a +2 and one of a -1 don't even each other out properly. So our first step, let's figure out the charge, and then we'll figure out how to put them together. So for the first one, I already did it for you. So sodium was a +1, chlorine was a -1. And just as a review, this comes from looking at where elements are located on the periodic table. Everything in group 1, the first column on the periodic table, forms a charge of +1. Everything in the second column is +2. We skip the transition metals. When we get over to boron, these are going to be +3. We don't have any +4s, so when you get to the next column, you should kind of pause a second. And then remember that if we're actually going the other direction, fluorine is 1 away from neon, so fluorine will become a -1, oxygen's a -2, nitrogen's a -3. So those are our 6 different families that we know the charges of. And if you just label those on your periodic table, now it should be pretty quick to look at each element and just fill it in. So for sodium, sodium's a +1. Sulfur is a -2. I'm just going to go down this column and continue on with that. So potassium is right here, so that's a +1. Fluorine over here, that's a -1. Beryllium is over here. Excuse me. That's a +2. Chlorine over here, that's a -1. And our last two are oxygen and aluminum. So oxygen's a +3, aluminum is a -2. So once we know the charges of these different elements, now we can kind of figure out, well, how do they fit together? The first thing we're going to look for is we're going to look to see if the positive and negative, if the charges, the number on them is equal. So we're going to look and see, are any of these the same number? And I see for the first example, a 1 and a 1. If they're the same number, they're what we call a perfect match. That means that they perfectly complement each other. And all I have to do to write the formula is take the two symbols, drop the charges, and squish them together. Overall, the charge of a formula is 0, because if I have +1 and -1, that equals out to 0. So I don't write any charges on my final formula, because my final formula should have a charge of 0. I'm going to look down the list. I see 1 and 2. That's not a perfect match. 1 and 1. This is going to be another example of a perfect match. So I'm going to just drop the charges and just push the two symbols together, K and F. So KF is our formula. 2 and 1, 3 and 2. So nothing else here is a perfect match. If the charges are not equal, then we're going to do a little bit of a shortcut, which I call crisscross. I gave the example up here. If something was a +2 and it was bonding with something that was a -1, that's not a perfect match, because this wants to give away 2, but this element's only willing to take 1. So if we know that a compound should end up being 0 in the end, that's what happens if they're a perfect match for each other. They've perfectly balanced out, and so overall the charge becomes 0. If we look at this example, I have to alter this a little bit to turn it into a 0 for the end. +2 minus 1 leaves me with just +1 right now. I would need to have another -1 so that I have 2 positives and 2 negatives to get to 0. What that tells me is whatever this element is, I need 2 of them to balance out with 1 of this element so that they perfectly match each other. The shortcut way of figuring out that formula is to do what I call crisscross. In this case, sodium's a +1, sulfur's a -2. These are not perfectly balanced. I need to have another sodium so that if I wanted to have a -2 for sulfur, 2 sodiums would give me 2 positives. And the way that I'm going to do that a little bit faster is I'm going to take these numbers that I see, the charges, not the positive or the negative signs, but just the numbers, and I'm going to crisscross them. I'm going to take them from the top of the element they're on, and I'm going to drop them down to the bottom of the other element. Again, this is just kind of a fast way of figuring out what number of each element do I need to perfectly get to that 0 point where they perfectly complemented each other. So in this case, for sodium, I always write the cation first, the first element, the positive one. So sodium, I'm going to need to have 2 of them. If each one of them has a charge of +1 and I have 2 of them, that gives me a total overall charge of +2 right now. And then I'm going to write my second symbol, which is sulfur, and I need 1 sulfur. We don't write 1s as subscripts. It's assumed to be 1 if we don't write anything. So if we had +2 for these 2 sodiums and the sulfur is -2, that equaled out to 0. And again, that crisscross method is just kind of a faster way of figuring out what the subscript should be without having to draw a picture and like do math on the side. So that's kind of our fast way. Okay. Next, we have beryllium and chlorine. These again are not a perfect match. Beryllium's a +2, chlorine's a -1. So I'm going to take those numbers from the top corner and I'm going to crisscross them. I'm dropping them down low to become subscripts. Beryllium gets written first. The beryllium I just need 1 of. I don't need to write 1s. And then the chlorine, I need to have the number 2 written down low. So 1 beryllium will bond with 2 chlorines, and that will become an overall charge of 0 because the beryllium loses 2 electrons and each chlorine takes 1, and that perfectly balances out. Last one on here, aluminum's a 3, oxygen's a 2, not a perfect match. So we're going to crisscross that. Aluminum is going to have the number 2 down low next to it. And then oxygen is going to have the number 3 down low next to it. 2 aluminums, each aluminum has a charge of +3. If there's 2 of them, then that means that the aluminums total have a charge of +6. Each oxygen has a charge of -2, and there's 3 of them. So that's a total of -6. So +6 and -6, that perfectly balanced out. All right, let's go ahead and take a look at this last little piece, which is about the naming. So when naming ionic compounds, the name of the cation, which is typically a metal, it's always written first in the name. So the cation was our first column. We always wrote it first in the formula, and we're always going to write it first in the name as well. So I'm going to go ahead and just name these. Na is called sodium. K is called potassium. Be is called beryllium. And Al is called aluminum. So that's the first part of the name. We just named the first element. The second part of the name is going to be the name of the anion, which is typically a nonmetal, but the ending gets changed to be IDE. And the reason why we do that is this tells us that it's not an element anymore, that it's actually in a bond as part of a compound. So that ending of IDE tells you it's a compound, not an element. For these, we're going to see some examples up here. The ending, kind of what the ending is, you're going to start to get familiar with that as you practice some of these. Our element here is S, and so S is called sulfur. So I'm going to start with sulf, but I'm going to change the ending, which is I'm going to change that into ide. So instead of sulfur, I would say sulfide. For our next one, we have the element F, which is fluorine. So I'm going to start by writing fluor, and then instead of ene, I'm going to write ide. So fluoride. Okay, so notice we're not adding this on. We're not saying fluorine-ide. We're not tacking it onto the end. We're actually changing whatever the previous ending is into ide. Next is chlorine. So instead of chlorine, I'm going to write chloride. And our last one on here is oxygen. So for oxygen, we got to kind of figure out what is the ending, and it's actually most of the word. So we're going to keep ox, but then instead of YGEN, oxygen, we drop off that last chunk and we change it to ide. Okay, so it's not oxygide or something, oxide. You've heard that, carbon dioxide, carbon monoxide, you've heard oxide before. All right, so we have a couple practice. Write formulas for the following compounds. So we have 4 of those to practice. So this is looking at what we did up here. So the first thing that we need to do is figure out the charge on each element so that we can figure out if they're a perfect match or crisscross. So these are my 2 pieces. I have aluminum and I have iodide, the element iodine. So those are my 2 elements. And then we're going to go ahead and find the charges of each on the periodic table. So aluminum is +3. Iodide is over here, which is -1. And once we have those written out, now we can look and see, are they a perfect match or a crisscross? They're not a perfect match because the number isn't the same. So if they're not the same number, then I'm going to have to crisscross them. So when I crisscross, I would get aluminum with just a 1 next to it. I don't need to write that. And then iodide would have a 3 down low next to it. So aluminum iodide is Al-I3. So we're going to go ahead and take a look at each of these. So calcium, and then phosphide is from the element phosphorus, potassium with the element sulfur, and sodium with the element fluorine. Okay. So pause this here and go ahead and look up the charges and then figure out what the formulas would be, and then hit play and continue on. All right, hopefully you paused it. So if we go ahead and check your charges, calcium's a +2, phosphorus is a -3, potassium's a +1, sulfur's a -2, sodium's a +1, fluorine's a -1. And I got those just from the periodic table, finding the elements, looking at the charges. When I look at these, this is not a perfect match. This is a 2 and a 3, so that's a crisscross. Ca3, P2. The next one, 1 and 2, again, not a perfect match, so we're going to have to crisscross them. K would get a 2 next to it. S is just 1. And for our last one, +1 and -1, that is a perfect match. So I just get rid of the charges and push the element symbols together, NaF. If we wanted to go the other direction, we're given the formula and we wanted to write the name. Remember our rules for naming. We name the first element, then we name the second element, changing the ending to ide. Be is the element beryllium. I'm going to just go ahead and name all the first elements. Na is sodium, Cs is cesium, and Sr is strontium. Okay, so name the first element. That part's pretty straightforward. For the second part, we're going to name the element, but I have to change the ending to ide. So the element H is hydrogen, and hydrogen sounds kind of like oxygen. So if you think about how we changed oxygen, we changed that to oxide. We got rid of the whole YGEN. So we're going to do something kind of similar for hydrogen. Okay, so for hydrogen, we're going to get rid of the vowel on after this. So and we're going to get rid of ogen and we're going to change it to ide. For the most part, we typically don't have two vowels in a row, so we don't say hydroide. So typically there's not two vowels next to each other. Chlorine will get changed to chloride. O is oxygen. That got changed to oxide. And then Br is bromium. I'm sorry, bromine. So we're going to change that to bromide. All right, so that is the end of that section. You have practice on the next page with more of these, but before we get to that, we have one more thing to add on here. But if you want to pause and do some more practice before you look at the next part, you can do the first 8 on the back for practice, and then look at this polyatomic section as well. So you can stop and do some practice, or just move on to this and then do all the practice. All right, so the one last piece we have to throw in here is we have something that are called polyatomic ions. Poly means many, and then atomic means atoms. And so a polyatomic ion is many atoms that, when they're together, have a charge to make an ion. And so if I have an ionic compound that contains a polyatomic ion, what that really means is that this is going to be a compound that has more than 3 different elements in the compound. But we still can only look at 2 chunks when we're talking about the name, or when we're talking about perfect match or crisscross. I can only have 2 pieces. So you have to kind of recognize, okay, if there's 3 different elements, then which chunks stay together as the polyatomic ion? All right, these compounds are named using the same rules above, except the name of the polyatomic ion doesn't change. No, I do. So there's a note on here. Your reference sheet has the list of polyatomic ions. So I was just checking to see. So they're on the back of the periodic table that I had printed. So this is on your reference sheet. Those different polyatomics are listed on here with their names. So these aren't ones you're going to have to memorize. You just have to look them up. Okay. Most of the polyatomic ions, their names have a specific pattern that you'll recognize over and over. So if you look at these names, you'll see acetate, carbonate, hydrogen carbonate, perchlorate, chlorate. You'll notice that a lot of these end with ate. That's a big hint that they're polyatomic. So if you see something that says 8 on it, that tells you look at your reference sheet. Focus that. Another thing that you'll see a lot of them end with, where we left off was here. So then we have chlorite, hypochlorite. So you'll notice that we see some of those ites as well. There are a couple exceptions on your reference sheet that don't end with ite. So cyanide is that IDE ending, hydroxide is that IDE ending, and then one that doesn't fit any pattern at the bottom here is ammonium. So we actually have 3. So cyanide, hydroxide, and ammonium are our 3 examples of polyatomic ions that don't end with ate or ite. If you're looking for cyanide on the periodic table, you're not going to find it. It's not an element. Hydroxide kind of sounds like hydrogen, but then it also sounds like oxide, which is oxygen. And so hydroxide is oxygen and hydrogen together. And ammonium, again, if you're looking for it on the periodic table, it doesn't exist on there. And again, reference sheet is where you find your polyatomic ions. If we wanted to name the following compounds, even though there's 3 or 4 different elements, calcium, chlorine, oxygen, magnesium, carbon, oxygen, barium, oxygen, hydrogen, etc., we only can have 2 words in a name. So we just need to figure out which chunk in this formula is a polyatomic ion, and then we're going to name the 2 pieces. When I look at this one, if you see parentheses, that gives you a pretty good idea that that's probably the polyatomic. So ClO3, right here on my reference sheet, is this. And that whole chunk has a name. So I'm going to name the first part first. Ca is calcium. And then I'm going to name the second part second. So ClO3, according to my reference sheet, is called chlorate. Once I do that, I'm done. I don't have to change the ending. I just wrote it down exactly how I looked it up on my reference sheet over here. I didn't change the ending, and we're done. Next, I have MgCO3. So I'm going to look and I'm going to see if I see anything that looks like that. And right here, I see CO3. So that CO3 is called carbonate. That tells me the second word in my name. Again, if I'm looking it up on the reference sheet, I don't have to change the name of it. The only thing I still have to do is name Mg, which is magnesium. There should be a space there. I ran out of room. Magnesium carbonate, 2 words. All right, next up we have Ba, and then OH is in parentheses. So if it's in parentheses, again, that gives me a pretty good hint that I'm going to find that on my reference sheet. So I'm going to go ahead and name Ba, which is barium, and then I'm going to find the name of OH. All right, and I see that right here, hydroxide. You might be asking, like, what about this 2? This 2 just tells me they weren't a perfect match, and there was crisscrossing that happened. But that's not something I have to worry about for the naming. The naming is just what are the 2 pieces that went together. All right, Li3PO4. So I'm going to look for anything that looks like LiPO4, Li3PO4. And I see that right here. So PO4 is called phosphate. That's this whole chunk. Now it's called phosphate. That's the second part. And then the first part, Li, that's the element lithium. So I can just fill that in. So again, the rules for writing names are pretty much the same. We just need to use the reference sheet. The last part is, what if we wanted to go the other way? What if we wanted to start with the name and we wanted to write the formula? So just like before, if we're given the name, I need to figure out what are the charge of each piece, the charges of each piece, and then perfect match or crisscross them. So I'm going to go ahead and start with sodium. That's the element Na. And I'm going to look up the charge for sodium. That's a +1. And then nitrate. And I underlined this as a reminder. If you see ATE, that means it's on the back. So I'm going to look for nitrate. And that is NO3. The 3 is down low. And then the charge is written at the top. So the NO3, and then the charge is just negative, which means -1. Once I have that written, I'm going to look at the charge, +1 and -1, and ask, are these a perfect match or a crisscross? +1, -1 is a perfect match. So I don't need to write the charges, but I'm going to take all the rest of it and swoosh it together. NaNO3. So notice that the 3 stays because that was part of what nitrate is. Nitrate is NO3. Like that whole chunk has to stay together. Okay. Ammonium, this is one of the 3 polyatomics that doesn't end with an 8 or an ite, but it is a polyatomic. So I'm going to look it up on here. Ammonium is NH4 with a charge of +1. So NH4 with a charge of plus, which means just 1 since the 1's not written. And then phosphate, when it ends with ATE, that tells me to look it up again. So I see phosphate right here. That's PO4 with a charge of 3-. I'm going to look at those charges, and I see they are not the same, so this is going to be a crisscross. So I'm going to start by writing NH4, and I needed to crisscross and write the 3 over here, but if I write it like that, it looks like NH43, which isn't right. I need this whole NH4 chunk, I need there to be 3 of them. So I'm going to put this in parentheses before I crisscross. NH4, I need 3 of them. For the next part, PO4, and if I crisscross, it would be a 1. I don't need to write that. So I don't really need parentheses around this. I don't need to write the 1 because I just need 1 PO4. And it's 1 if we don't say it otherwise. Okay. All right, the element potassium is K. It has a charge of +1 from the periodic table. Chromate, I look up on here, CrO4 with a charge of -2. When we look at these, +1, -2, those are not the same charge. So that's going to be a crisscross. Okay, I need to have 2 of them. Remember, we don't write plus or minus. Subscripts are just counting, so I don't write +2 or -2. It's just I have 2 potassiums. And then next, CrO4, I just need 1 of them, so I don't have to put parentheses. I don't have to write a 1. It's assumed to be 1 if I don't write anything. Calcium is just an element. From the periodic table, I know the charge is +2. And then carbonate, when it ends with 8, I gotta look it up on here. That's CO3 with a charge of -2. And when I look at these charges, +2, -2, that's a perfect match. So I'm just gonna get rid of the charges and squish the 2 parts together. Ca and CO3 are a perfect match. Last one on here, aluminum is an element, so I'd look it up on the periodic table. It has a charge of +3. And then hydroxide is one of our 3 polyatomics that doesn't end with 8 or ite. That's an OH with a charge of -1. These are not a perfect match, 3 and 1, so we're going to need to crisscross. And when we crisscross for this, aluminum, I just need 1, so I don't need to write that. And then hydroxide, that OH chunk, does need to have a subscript of 3. Remember, before I crisscross for a polyatomic, the polyatomic has to go in parentheses, and then I can write the 3, because I need 3 of that entire chunk. If I just write AlOH3 and I don't put parentheses, that would mean that I only have 3 hydrogens, but the oxygen didn't get tripled. It was just 1 oxygen, and that's not right. Okay, so we want to make sure that we have those parentheses to show that it's the whole hydroxide ion that got tripled, not just the hydrogen. On the next page, page 4, you will see practice problems. So work on those, and I'll leave a key so that you can check your answers. Work on practicing writing formulas and writing names on page 4 of your packet.